We humans tend to like to construct convenient boxes to describe the universe we see around us. Consider the manner in which we divide the sciences: physics, chemistry, biology. Neat, convenient, little compartments like specimens in a case. In reality, of course, the universe we live in is a lot more messy. For example, to truly understand a complex system like the Earth, we can't rely on any one of the traditional sciences, but have to call on them all collectively to describe the interconnecting, ever-evolving planet from differing perspectives. So, in this episode, let's look at another way of considering the evolution of our planet, a perspective that has a focus not on the evolution of life, but on the evolution of Earth's minerals. A perspective that considers how minerals have influenced all Earth's systems, including the biosphere and its history, as revealed by paleontology. Today, there are around 4,400 known minerals. The crust of our planet is composed of around 90% of minerals we call silicates. These are minerals that contain a silicon molecule composed of one atom of silicon bonded to 4 atoms of oxygen in various configurations, with other elements like aluminum and calcium. One of the most common minerals is feldspar. Another very common silicate mineral in the crust is quartz, a mineral composed of the silicate molecule bonded just to itself in a 3-dimensional structure. It is important to note that the majority of minerals, unlike the images you see in books or in museum collections, do not occur as these large and beautiful showy crystals, but are usually found as a mosaic association with other minerals in rocks. Rocks are effectively just aggregates of various minerals. Only around 8% of the Earth's crust is composed of non-silicates such as oxides, sulfides and carbonates. Carbonates, and in particular the mineral calcite, have been vital in the evolution of the biosphere. The crust, though, only represents just 1% of the Earth's total volume. Below the crust, down in the mantle, are silicates rich in magnesium and iron. For example, olivine. Olivine is common in rocks like peridotite, a heavy rock reflecting its higher iron content. By the time we get to the Earth's core, the main constituents are iron and nickel, liquid till about 2,890 kilometres below the Earth's surface, and then present as an iron-nickel alloy to the centre of our planet. This picture I've just painted is the result of over 4.54 billion years of planetary evolution and has had profound implications for our understanding of Earth's biosphere. So in this episode, I want to consider the mineralogical evolution of our planet. So let's consider, what are the very first minerals? Which minerals develop after the Earth had formed? And how do we reach that wonderful diversity of minerals we see today? And what role would life have to play in that story? The idea of looking at our planet through the lens of minerals was developed by Robert Hazen of the Carnegie Institute. Hazen and his colleagues from various research institutions proposed that many of the 4,400 minerals we know of today co-evolve with the biosphere through time. Obviously, minerals don't mutate and evolve in a biological sense, but they have changed over time, both reflecting and influencing our evolving planet. As such, considering the changing mineral makeup of our planet also helps paleontologists appreciate factors that might be influencing the fossils they find through Earth's history. They proposed 3 eras and 10 stages of Earth's mineral evolution. Each stage sees dramatic changes in the diversity of Earth's near surface, that's recoverable minerals. That might explain why Hazen's ideas were also covered in The Economist. Incidentally, Bob Hazen is also a great courses alumnus who presented a show on the origin and evolution of the Earth in which he expands these ideas further. Why don't you check it out? But let's start in our story where the book starts right at the beginning. In the beginning, there were no minerals. By this beginning, I mean the very beginning, some 13.7 billion years ago at the Big Bang. It's estimated that about 377,000 years after the Big Bang, the first hydrogen and helium atoms started to form. And probably by about 560 million years after the Big Bang, stars would form from the collapsing clouds of these gases. Ultimately, the death of these during supernova would seed the universe with heavier elements that had formed by nuclear fusion in the hearts of these first giant stars. It is likely that during these cataclysmic events, some of the first microscopic crystalline minerals, around a dozen or so, would form, including diamond, graphite, and various silicates. These few primordial minerals had been named minerals by Hazen, a reference to the ancient Sumerian city of that marks some of the earliest evidence of complex civilization. These early minerals would combine, mix and react over time to form much of the complex world we know today. To understand the mineral story of Earth, though, we have to move quite a way forward in time to about 9 billion years after the Big Bang. That's 4.6 billion years ago. This is a time before our familiar planets had formed. In their place was a vast cloud of hydrogen, helium and dust. The dust probably comprising some of those early minerals. This cloud was contracting and spinning under its own gravity, forming a concentration of material at its centre. This is known as the T-Tauri phase of a star's development. The star not yet able to fuse hydrogen and initiate nuclear fusion, but still bright and radiant as it collapses under its gravity. Even at this stage, though, it is still energetic and hot, with the young protostar heating up a disk of material that surrounds it. This is the protoplanetary disk, and it's from this that the planets will eventually form. It is thought that around 60 mineral species get cooked in this particular stage of the solar system's development. Wouldn't it be wonderful to glimpse into those early times around 4.6 billion years ago? Well, we can. Because some of those early mineral phases had been preserved and occasionally fall to Earth as a class of meteorites called primitive chondrites. These developed as the dust and sun-bathed minerals started to accrete together, initially due to electrostatic attraction, a bit like dust bunnies under your bed, and later as they get larger under gravity. An interesting feature of these meteorites are the small, about 1 millimeter spherical chondrules. These probably represent molten droplets that were formed by flash heating as the early sun cooked the materials in its surrounding protoplanetary disk. Fascinating echoes of early conditions in that early cloud before the Earth was born. Over time, these small chondrites would accrete together to form larger bodies. If larger than about 200 kilometers in diameter, heat from decay of radioactive isotopes trapped inside these rock piles and heat generated by collisions would cause the interiors of these larger bodies to melt, at least partially melt anyway, and produce new suites of minerals. These so-called planetismals would also differentiate under gravity, with heavier components like nickel and iron sinking to the centre of the mass. This creates a protoplanet with a basaltic, relatively light lava-like crust surrounding a dense metallic core. Meteorites called achondrites are thought to represent the shattered crustal fragments of some of these protoplanets. Iron-nickel meteorites are likely the shattered metallic cores. This also tells us that the early solar system was a busy shooting gallery with multiple mergers, titanic collisions and destruction of some of those early planetary bodies. By the end of this stage, and all this activity would see the cumulative count of minerals rise to about 60. We still obviously have quite a long way to go yet, though. After the Earth had formed and differentiated, the light scum of less dense minerals that remained close to the surface would have cooled to form a skin, a bit like the skin on your cocoa. Its composition would have been similar to basalt that we find today in places like Hawaii. This period is sometimes referred to as the Black Earth, reflecting the blackened basaltic surface that would have characterized our planet at this time. When I visited the big island of Hawaii in 2015, I really got a feeling for what a strange and alien place that early Earth must have looked like. This black crust would be repeatedly recycled, though. melting and generating magma that would undergo an important process called fractional crystallization. As magma cools, its composition changes. This is because different minerals crystallize out of the melt at different times, depending on their melting point. For example, olivine, having a high melting point, will be the first mineral to crystallize and settle to the bottom of the magma chamber. As olivine has now been removed from the remaining magma, the composition of the remaining molten component has been changed. As the magma continues to cool, minerals crystallize out in the order of their melting point, continually changing the composition of the remaining magma and the composition of the minerals it generates. This stage of magma differentiation is probably the level of mineral evolution that the Moon and Mercury reached, but went no further. It is probably the presence of liquid water on Earth that would let mineral evolution progress even further, though. It is possible our planet may have been cool enough for liquid water, we think, at around about 4.4 billion years ago. The interaction of minerals with water would raise the number to about 500 in the Earth's system. This will also be possibly the stage that the once wet Mars might have also reached. But another significant development would be the formation of granitic rocks, rocks that contain a lot of quartz and feldspar, which started to form in Earth around about 4 billion years ago. As magmas were continually injected into the early crust, they would partially melt the surrounding crustal rocks, but with only the relatively less dense minerals melting, as it is these that have the lowest melting points. As a result, these magmas had a very different composition of less dense minerals than the parent rocks that were melted to form them. It is this process that would produce the granitic magma that would rise into higher levels of the crust, cool, crystallize and form granites, like you might find in your kitchen countertop. Because granites are significantly less dense than basaltic rocks, they're about 2.7 versus 3.3 grams per cubic centimetre, they're very buoyant and tend to float on the surface of the dense rocks in the mantle. These accumulations of buoyant granitic rocks would be the seeds of the first continents. Granitic melts would continue to differentiate, helping concentrate rare, mostly lighter elements such as lithium, cesium, beryllium and boron into granitic rocks like pegmatites, which many rare gems and minerals form from. Through these processes, our mineral count is now around the 1,000 mark. Earth, and possibly Venus, reached this stage of granite production and mineral evolution, but our own planet, probably uniquely in the solar system, would have many more stages to pass through before its current final inventory was reached. The next stage is a significant one. It involves the initiation of a process which, at the moment, we think is only found on our planet, at least in our solar system. That's plate tectonics. Plate tectonics describes the large-scale motions of the fractured plates that make up the Earth's outer surface, what we call the lithosphere. At plate boundaries, lithosphere can slide past each other, as is the case along the San Andreas Fault in California, but can also spread apart, generating new oceanic lithosphere, as occurs along the Mid-Atlantic Ridge. Some boundaries are marked by the collision of plates, either forming large mountains like the Himalaya of northern India and Nepal, or by plates being destroyed as one is physically forced under another in a process that we call subduction, as is occurring along parts of the western edge of North America today, generating the volcanic activity of the Cascade volcanoes like Mount St. Helens and Mount Rainier. As I already mentioned, as far as we know, Earth is the only planet to have initiated extensive and prolonged plate tectonics. Plate tectonics is a significant reason for the complexity and diversity of Earth's geology and its biosphere. The temperature and pressure regimes caused by different types of plate movements generated new minerals as well. Plate tectonics would also elevate mountains, exposing these newly formed minerals to weathering process and generating even more minerals. This is a process still going on today, like you can see here in Scotland, with rocks that were once formed deep in the Earth's crust now exposed and eroding at the surface. In addition, oceanic water seeping into the crust at those ocean crust generating mid-ocean ridge systems, and also though taken down into the mantle on those subducting slabs of oceanic lithosphere, would alter pre-existing rocks, creating even more minerals. This is an ongoing process that is still occurring at mid-ocean ridge hydrothermal vent systems today. It is at vent systems where metals, particularly copper and zinc in combination with sulfur, generate massive sulfide ore deposits. These processes have concentrated large quantities of metal ores. For example, copper and zinc in the Kidd mine near Timmins, Ontario, was originally a hydrothermal vent system on an ocean floor over 2.7 billion years ago. All this plate tectonics related activity brings our mineral count now to an impressive 1,500. Impressive, yes, but still a long way off our current 4,400 mineral species. How do we almost triple the diversity of minerals on Earth? So, in summary, it would appear that 1,000 mineral species would be a common tally of minerals for many rocky planets and moons in our solar system, and probably other solar systems too. Plate tectonics boosted that to 1,500 in the early Earth. But it is probably the presence of abundant and very evident life that we need to examine to explain the overwhelming bulk of the 4,400 minerals on our planet today. This is where the stories of mineral and biological paleontological evolution march forward, hand in hand. We have paleontological evidence of life at around 3.4 billion years ago. Bacteria metabolizing sulfur-based compounds living among grains of sand on a beach in what is today Australia. It would appear, however, that life initially, even when we have this fossil evidence, had very little effect on increasing the mineralogical diversity of our planet. That would change though, and change dramatically, about 2.5 billion years ago when we start to see significant numbers of certain microbes spreading across the planet. Microbes like these modern examples that have developed a neat little photochemical trick: photosynthesis. Their presence at this time can be seen in specific features that they left behind in the sedimentary rock record, called stromatolites, that we covered in our lecture on trace fossils. These interesting structures form as mats of photosynthetic bacteria trap and bind fine-grained sediments. The earliest form of photosynthesis used hydrogen sulfide as a hydrogen donor to power this reaction, but later forms of photosynthesis would use water. The consequence of this would be the release of a dangerous byproduct, well, dangerous to any life that evolved in conditions in the early Earth, and that byproduct was oxygen. It wasn't just photosynthetic bacteria and stromatolites though, there would be plenty probably of photosynthetic organisms living in the water column as well. This period of history is known as the Great Oxygenation Event and is probably the single most important event in the diversification of Earth's mineralogy. Of the approximately 4,400 known mineral species we have today, over half of them are oxidized and hydrated products of other minerals, a situation that can only develop on a planet rich in free oxygen. For example, 256 of the known copper oxide minerals, such as the beautiful malachite and azurite, form from weathering in an oxygen-rich environment. It is at this point where we see the diversity and complexity of minerals outstripping anything else in the solar system. This is a wonderful example of Earth system science, the biosphere, life, producing and co-evolving with minerals in the geosphere. Another consequence of this availability of oxygen would be a dramatic change in the chemistry of the oceans. Prior to the Great Oxygenation Event, the Earth's oceans had been largely anoxic, that is, they contained little to no dissolved oxygen. As a consequence, Fe2+ iron, that is, in unoxidized iron, was the common form found dissolved in seawater. With the introduction of oxygen into this system, that Fe2+ iron was oxidized into insoluble minerals like magnetite and hematite. These would effectively form rust in the oceans that would settle out in layers on the ocean floor of the continent shells, alternating with layers of slightly less iron-rich chert or jasper. These so-called banded iron formations are some of the most iron-rich ores on Earth today and are the result of this significant change in the Earth system around 2.3 billion years ago. At around 1.85 billion years ago, the deposition of banded iron formation ceases abruptly. The reason for this is greatly debated, but for an interesting possibility, we need to travel to the town of Sudbury in Ontario. Sudbury, home of the Science North Interactive Museum, the Sudbury Wolves hockey team, Jeopardy host Alex Trebek, and the world's largest nickel. The reason behind the big nickel is the association this town has with nickel ore. The nickel ore and other valuable metals such as copper and palladium are concentrated in an oval structure about 62 kilometres by 30 kilometres wide and over 15 kilometres deep that's called the Sudbury Basin. The basin was likely more circular when it formed about 1.85 billion years ago, but has subsequently been deformed by plate tectonic processes. Interpretation of this structure was much debated. Some favoured a volcanic origin for this crater, but geologists in 1970 collectively decided that what they were looking at here was a massive impact crater, a crater now known to be the second largest still present on Earth's surface. Sudbury, 1.85 billion years ago, lay on the southern margins of a large continental mass called Nina. If you could have travelled back there, you would have found a barren landscape crisscrossed by large braided river systems. But what of that fateful day? The impacting body, probably about 10 kilometres in diameter, would have entered the atmosphere travelling around 8 times the speed of sound. It impacted off the southern shoreline of Nina, digging a vast hole many miles into the Earth's crust. It's been estimated that around 2 kilometres of crustal material was ejected, forming a crater that was originally 250 kilometres in diameter. Debris hurled out from that crater, covering an area of about 1,600,000 square kilometres, with debris being found over 800 kilometres away in Minnesota. It's been estimated that the ocean waters, pushed out of the way by this impact, would have created an enormous tsunami at the impact site, maybe up to 1 kilometre high, and still 100 metres high, over 3,000 kilometres away. Some of that material blasted out of the crater that we call ejecta, returned to Earth and covered the impact area in a layer of fractured rock over 2 kilometres thick. In the impact crater, deep under all that impact debris, magma would slowly rise and cool slowly. As it cooled, heavy minerals started to settle out of the magma, forming a layer at the bottom of the structure. It's here where the richest ore is found today. All right, but what does this have to do with the end of the unique biological mineralogical association that resulted in the formation of banded iron formations? An interesting, yet still much debated hypothesis was suggested by John Slack and William Cannon of the United States Geological Survey in 2009. They point out that many of the banded iron formations are found directly below the Sudbury ejecta layer, but very different rocks appear to be deposited after the impact. Something, according to the authors, had changed in the ocean system after that impact. They suggest that the tsunami, falling debris, and large underwater landslides that would have been triggered by the impact could thoroughly mix up the ocean and deliver a pulse of oxygenated surface water into the deep ocean setting. This, they suggest, would have ended the supply of that Fe2+, that dissolved iron from the deep ocean into the shallow continental shelves where most of the banded iron formations were being deposited. This ending, with a few exceptions, a unique biochemical mineralogical system. As I said, this is still a controversial hypothesis. Some note that although banded iron formations disappear, other iron-rich sediments are deposited after this event. In addition, due to difficulties in correlation, it's still difficult to be certain that banded iron formations further away from Sudbury are not in fact younger than the impact event. As a result, not affected by the impact. Whatever happened, And whatever the exact timing of the end of banded iron formation deposition, on a geological timescale, banded iron formation deposition does end rather abruptly. This change also marks the transformation of the land, as oxygen, now no longer captured to form rust in the oceans, is released to the atmosphere and would start to oxidize minerals on the continents, turning many parts of the surface red, just as it still does in parts of the world today. What follows from 1.8 to 1 billion years ago is what is known unofficially as the boring billion. This boring billion, well, actually more like 800 million years, sees no new major innovations in life or minerals. But the history of life is a bit like war. Long periods of boredom with sudden and short snaps of terror. The terror this time would eventually come in the form of ice. Between 1 billion and 542 million years ago, the Earth would suffer a series of superglaciations or snowball Earth events. For most of this time, the continents were grouped together around the equator in a supercontinent called Rodinia. But by about 830 million years ago, that continent had started to fragment. During fragmentation, shallow seaways opened up into the continental interior. It's been proposed that this situation would have caused intense rainfall in the tropics as these shallow warm seas started to evaporate in the tropical sun. As this progressed, the rocks on Rodinia would start to undergo intense tropical weathering. That is, weathering that uses carbon dioxide dissolved in rainwater to convert all those silicate minerals in rocks into clay minerals. These minerals were transferred to the oceans, effectively washing carbon dioxide, the Earth's greenhouse gas, out of the atmosphere. As the Earth's greenhouse blanket thinned, temperatures dropped and ice advanced from the poles. According to Paul Hoffman of Harvard University, once ice reached a latitude of what is today about Texas, a positive feedback loop would be initiated, with more sun being reflected back into space than could be absorbed by the planet's surface, causing temperatures to drop even faster. This would generate even more ice that would eventually overrun the equator. At least 2 snowball Earths would develop, each persisting for millions of years. Earth would have resembled a vast white cue ball from space. Things would change though. Volcanoes would occasionally break through the ice and deliver a belch of carbon dioxide into the atmosphere. With no ocean to dissolve into or rocks to weather, carbon dioxide built up to extremely high concentrations. This created a super greenhouse climate which would cause the snowball to collapse catastrophically and end rapidly. These snowballs would also have implications for mineral evolution too. It is thought that the end of each snowball would be associated with extreme weather conditions. These so-called hyperhurricanes would thoroughly mix the oceans, flooding them with nutrients and causing a bloom of oxygen-producing cyanobacteria. The resulting increase in the availability of oxygen provided opportunities for creatures to evolve bigger bodies. This would set the stage for our next leap in the Earth system, the explosion of multicellular life forms. By the time we get to the base of the Cambrian period, 542 million years ago, biology would be the main driving force in the formation of new minerals. The Cambrian would see a proliferation of creatures with biomineralized skeletons composed of calcium carbonate, calcite, phosphate, apatite, silica. The colonization of the planet by organisms, and in particular the movement of plants onto land, would see a vast increase in the amount of clay minerals being produced by biological weathering. Particularly important would be the effect land plants would have on the development of new types of organic-rich soils and the opportunities for more mineral formation. This expansion of the biosphere and organic carbon production would see the formation of more carbon-rich deposits too, deposits like black shales, coal, oil and natural gas. The explosion of biologically driven mineralogy would increase the total number of mineral species to the current level of 4,400, a product of our planet's long and complicated evolution and the prolonged development of its biosphere. A situation that, as far as we know at the moment, is unique in the universe. It is possible, though, that a rich mineral heritage is a fingerprint of life. Could this be used to search for biospheres on other planets? A complex mineralogy can be seen as evidence of a complex system evolution. As we have seen, the evolution of life on Earth significantly increased its mineralogical diversity. Perhaps in the future, in addition to the search for liquid water, the search for a larger mineral vocabulary will also help us zero in on extraterrestrial life and other complex biospheres.